Our final presenter will be Dr. Chad Mirkin from Northwestern University, and he will speak to us on methods of nanofabrication.
We have to go to number 4. Okay. Let me begin by saying, I think the comments that Dick started with were really somewhat inspirational to me as well. I mean, he talked about many people in the audience and the symposium having an impact on him. When I think about my own career, I think he was very generous to me, including me in that group. He was actually the person who had one of the greatest impacts on me, because he probably doesn't remember it, but I met him before I left Penn State to do a postdoc with Mark Wright and to go into war. And learn new areas going beyond my synthetic training. I was trained as a synthetic organometallic chemist, and he reassured me that this was a really good decision to make, that you'll hear all sorts of strange stories, but you'll experience some of those, and you will also learn incredible things. And we didn't overlap much, but we stayed in touch for quite some time. But his footprint on the group, and then footprint in science has had a very lasting impact in my career. And I think of what I chose to ultimately do and what I'm going to tell you about today, which is to move into this field of miniaturization and to begin to look at how chemical systems are influenced by miniaturization. Much of that came through some of the inspiration I got out of my experience at MIT and many of my conversations with Dick. So I'm delighted that Pittcon once again does a beautiful job, I think, of identifying great people for this award. And in Dick's case, they recognize somebody who has just moved across the gamut of science and had a lasting impact everywhere he's been, ranging from electrochemistry to bioanalytical chemistry and his work with sensor development, and also in nanoscience and nanofabrication. So congratulations. I'm going to tell you about something that we've been working on now for quite some time, but I think many of you haven't heard what's really happened over the last few years. I haven't talked about much of this at Pittcon, in fact, I think for 6 or 7 years. And that's this idea of trying to create nanofabrication tools. And I think if you look at this slide, I like to use this as a motivating slide because it's kind of our mantra at Northwestern. These tools revolutionize the world. They revolutionize the world in terms of how we transfer information, in terms of the printing press, for example, how we make electronic devices, computational devices, and they're beginning to impact many aspects of biology and medicine as well. The fact of the matter, though, is we now take for granted that the printing press can be effectively at every desktop in the world, in the modern world. And in fact, some of us expect to have multiple tools in the form of desktop printers. And this ability to rapidly prototype and make structures, documents that you would ordinarily have to take to a professional print operation at the point of use is just taken for granted. And it really begs the question, will one day we have the same in terms of microfabrication capabilities and also nanofabrication capabilities? Will we ultimately have tools that allow us to rapidly prototype on demand without having to go to an outside fab? Can we ultimately create a true desktop fab capability? And this was kind of motivation for the group where, frankly, maybe the way Dick was explaining how they approach problems, we weren't really sure we're ever going to solve the problem, but it's always good to put something out there as something that's really difficult to do and see how far you get. And the way we entered this area was through this discovery and what I'll call invention and development of this technique called dip pen nanolithography. So in 1999, I had a postdoc named Richard Piner who was studying water transport from an AFM tip to a surface and studying the dynamics of that process. And he discovered, first of all, that you, under certain conditions, could image the meniscus. And also under certain conditions, you could form add layers on surfaces or depletion layers, depending upon the relative hydrophobicity of tip and substrate. And he was very interested in the physics of that phenomenon. But as a chemist, especially as a synthetic chemist, I said, look, Richard, no chemist is going to care about this unless you can make things using this type of technique. And so why don't we start thinking about putting molecules in place of that water on the tip and use those molecules as ligands that can chemically react with an underlying substrate? And so that was kind of the birth of this field, where we took advantage of what was really considered a lemon in this whole field, and that was the capillary effect, the fact that water condenses at the point of contact when a tip is brought in contact with a surface in air. And we used that water as a carrier solvent to move these molecules from the tip to the underlying substrate. And so just via Le Chatelier's principle, you're driving the chemical equilibrium toward the substrate through the chemical reaction. It's a self-limiting process. And the beauty of this, of course, is that you have the resolution of an atomic force microscope. And you can begin to at least make custom architectures, not over large areas and not very many of them rapidly, but you could make some pretty interesting nanostructures out of a lot of different types of molecules, because it turns out this is extremely general, of course. As long as you can have compatibility between the tip and substrate and also the water meniscus, you can even flip out different types of materials by going to controlled humidity or controlled environmental chambers. We've done that, and you can use that to regulate how fast the molecules move from tip to substrate. But the big challenge, of course, was this issue of speed, that this was a relatively slow process. And so a lot of people, kind of criticized that. But looking back at this, if you think about why was this so interesting, and I'll tell you why it's interesting from my perspective and why I think it's ultimately very enabling. This wasn't the first time somebody did lithography with a scanning probe instrument, but it was the first time anybody directly delivered materials to a surface. And it was kind of a paradigm shift in the scanning probe arena, in the sense that prior to this, everybody was using kind of the mantra of the semiconductor industry was, let's deliver energy to a substrate, let's destroy it to destroy a resist or treat a resist, and then use that for subsequent functionality or subsequent reactivity. So in this case, instead of delivering energy and developing a surface and modifying a surface through a destructive type of methodology, we were using a constructive type of technique and taking advantage of this ability to directly deliver molecules and build add layers up out of many different types of materials. Now I'm going to fast forward. So this is not the only way to make nanostructures and microstructures on surfaces. The two areas that I think have gotten the most in terms of development and ultimate use, one developed by our previous speaker, George Whitesides and his group, microcontact printing, very powerful approach in terms of making structures that can be used for research purposes and maybe one day ultimately production purposes. Idea that you can take a stamp and coat with molecules and directly transfer to a surface, very powerful, massively parallel, but somewhat limited in terms of resolution, very limited in terms of registration capabilities. Dip pen was not a competitive type of technology for that. In fact, I would call it highly complementary. In the sense that dip pen had sweet spots that microcontact printing didn't have. It also had limitations that microcontact printing didn't have. One is it allows you to make nanostructures routinely. We can work sub 50 nanometer pretty routinely with the right types of cantilevers. We can build structures with almost perfect registry. We could parallelize to some extent. We went through an exercise where we began to build very large arrays of cantilevers, which was, again, what people thought about doing, even taking a page out of the millipede, for example. A lot of different considerations have to go into play when you're, though, transferring molecules instead of energy. We developed those capabilities, and many of them actually became commercial. But in the process, dip pen became a lot more complicated. And so one of the charms, one of the attractive features of it, at least from my perspective, and I think many people that used it, was that it was a relatively simple process. You could get up and running and make structures routinely and rapidly out of lots of different materials of interest with this very, very high resolution. We had built the largest cantilever arrays ever built, 55,000 cantilevers, working cantilever arrays, 55,000 cantilevers in a square centimeter. We'd published them, and that was kind of a tour de force accomplishment in the scanning probe arena. But as I said, as we did this, we began to build greater and greater complexity. And we were almost ready to just say, okay, we're done. Let's move this over just to the commercial side of things and let those folks run with it. And we had another idea. And the idea was, let's look at these two techniques and ask, how can we develop a way to take advantage of both of their strengths, or all of their strengths, and in the process, eliminate many of their weaknesses? And that was the birth of something we call polymer pen lithography. And I think this is a very interesting story, because it's one of those stories of sometimes, you go down a particular path, you have to step back and ask, what are we doing right, what are we doing wrong? Is there a completely different way of doing things that would give us a chance to move forward very rapidly? And that different way was a new architecture. It was, let's get rid of the cantilevers. This was the idea. Let's eliminate the cantilever. Cantilever is just a spring. let's move the spring to the tip. How can we do that? We can do that with a polymeric material. We could make a stamp, a la microcontact printing, of pyramids. But we can't use that stamp directly because it actually deforms too much in a scanning probe type of experiment. You have to mount it on a transparent, hard substrate, and that's going to be critical. So this is the type of architecture then that opened up a whole new area of science for us, and also engineering as well, because it created a whole series of capabilities that I want to share with you that I think are going to lead to this ability to have a true desktop fab capability. Okay, so let's look at the first example here. So this was the first system that we made. Very simple to make this particular architecture. You take a silicon substrate using really simple photolithography. In one shot, you make a mold. That mold is just a bunch of holes that are anisotropically etched. You lift off the resist. You fill with elastomer, put the glass substrate on here, cure, peel this off, and now you have a stamp of pyramids mounted on a hard, transparent substrate that now is inserted into a conventional scanning probe instrument. And we're going to use then these tips as point sources to deliver molecules to an underlying substrate. Of course, the beauty of this is it's also dirt cheap. Once I make one of these, I can make really a zillion of these, and very scalable. You can see here 11 million pyramids in a structure the size of a conventional silicon wafer. I think that one day there will be enormous sheets of these used to do a lot of nanofabrication and microfabrication over very large areas, as I'll show you in a second. So this was actually the first experiment with the first array. I was shocked that it worked so well. We coated these with alkane thiols. We deposited onto gold. And if you look here, we made 44 million features, 11 million at a time, in the form of these 4 dots that were duplicated over and over and over again. Okay, and again, if you scan over the entire substrate, there are very few examples of defect. Again, pretty extraordinary given the fact that none of this has been optimized in terms of alignment and getting these types of structures in contact in a uniform way. Then my students came to me and they showed me this. They said, look, this is really neat. The Beijing Olympics were going on, so they made the Beijing Olympic logo. And what was really cool about this was not just the reproducibility. These 15,000 replicas made simultaneously using this type of technique, where it's done in dot matrix type of form, where the runner is made with 600 nanometer dots, but the Beijing 2008 and the rings were made with 90 nanometer dots. And that was a shock to me, because I haven't told you one of the big problems with dip pen. With dip pen, you either work with small structures or you work with large structures. You don't go back and forth because it's a diffusion limited technique. Here, they were able to do this in a matter of minutes. Okay, and so the question, of course, was how and why. They also showed then they could make integrated circuits, where you could go from millimeter scale pads, microscopic leads, to nanoscopic electrodes. And as I'm going to show you, you can make a lot of very functional devices using this as well. This is the reason. It's something we had not anticipated, but understand now after the fact. This is an incredibly forgiving architecture, and so I can't emphasize the architecture enough. When you create this soft stamp on this hard backing, you create a structure that can be brought in contact with the surface. And this is why everything is so uniform. Much of the initial contact force is absorbed by the base. There's very little deformation when you bring the tips in contact. That allows you to get them all in contact. But once you do that, you begin to enter a regime where now you uniformly deform the tips. You're basically compressing them. And if you look, you go from circular dots to square-like features, and the harder you press, the larger the feature. And so that's how they were doing this. They were going back and forth between these 600 nanometer and 90 nanometer features simply by controlling contact pressure. This has now been modeled extensively, and we use it in an automated fashion in the lab with a scale, actually, to measure contact force and to dial in the feature size that we want. What else can you do with this? Well, one of the things that's interesting about this technique is the wells used to make the tips can also be ink wells. And remember that although these are nanoscopic in terms of sharpness, the wells are microscopic in terms of size. So we can use a normal inkjet printer and easily fill them with different types of chemical reagents, in this case 4 different proteins. And if you get 2 pens in here, you get 11 million pens if you're working with an 11 million pen array. So the challenge of putting different types of chemicals on tips becomes a lot easier using this particular approach. And so these are just proteins that have fluorescent dyes, and now we are patterning, and you can see as we go from left to right, we're going from, I believe, 65 nanometer protein features to 360 nanometer diameter protein features. As I said, this is a modelable and reversible phenomenon. If I push, you see I flatten. If I pull away, I go to smaller features. You can model this, and in fact, there are two different regimes in terms of the compression modulus. There's an initial less resistant phase with respect to the PDMS, but once you actually align the polymeric structures, you get into a stiffer phase. You have to take that into account in terms of modeling what contact force is going to give you a given feature size. And we've done that. You're basically just using a geometric model here and looking at how contact force blunts the tip and takes a deeper and deeper slice of the pyramid. If you're kind of following this and you do any work in this area, you should be thinking, how in the heck do you get all these tips level with the underlying substrate? That is a big problem. That's, again, something people often don't talk about in the whole scanning probe arena. And here's the problem. If I'm not perfect in terms of theta and phi here, just a few hundredths of a degree, 7/600ths of a degree, we go from a situation where this tip is in contact, and this one is many, many microns away from the substrate. Okay, so over large areas, this is a very daunting task. One of the things we did was we modeled this, and we asked, when should the contact force be the greatest? And it turns out when all the tips are level and in contact with the substrate. There's actually a global maximum in terms of contact force that comes out of the modeling. So we began to explore this idea of putting a scale underneath the substrate and then using an ordinary balance in this case to measure contact force. You adjust the tilt screws. So in this case, you can see you can adjust theta, and you get to a local maximum in terms of contact force. You keep it fixed, you adjust phi, and you get to now another local maximum. And then if you tweak it a little bit more, you get to what we call the global maximum. And at that point, we've now used that particular approach to level the array and create a system that's capable of doing the things I just showed you, but also this. If you look now, if we coat these with molecules, a pattern on a gold substrate, these are alkane thiols deposited onto a gold thin film on silicon. You can see when it's perfectly level, look at the features, less than 10% variation in feature size. This is across 1 square centimeter, so 15,000 tips in an array. Intentionally misaligned by 100th, small, medium, large. Flip it around by 100th of a degree, large, medium, small. I mean, this tells you have to be perfect in these types of experiments if you want them to work. And so to me, this is a big movement in this area in terms of solution to one of the real limiting factors in terms of not just these arrays, but all sorts of tip arrays that are designed for scanning probe lithography purposes. So what can you do with this? Well, one of the things that you can do is you can begin to pattern all sorts of molecules and substrates, and you can build all sorts of interesting array-type architectures. And one of the questions we had was, could we begin to pattern proteins on surfaces, and in particular adhesion proteins, and ask the question, does a certain type of feature size or presentation of certain classes of proteins allow you to systematically affect a cell differentiation event? And so in this case, we were looking at differentiation in neurogenic, myogenic, and osteogenic cells. And this was the idea. The idea was, let's, again, step back and ask, what do we have? We had spent all this time up to this point developing a way to level the array. We said, what would happen if you intentionally misaligned the array? And we can do that in a controllable way. Well, that will give you a gradient of features. And now you can build a combinatorial library of structures that vary in composition, size, interfeature spacing over a large area substrate very, very rapidly. And so we developed ways of doing this to immobilize molecules, in this case carboxylic acid terminated types of molecules, MHA over here. We can passivate with things like PEG, and we can build arrays of different sized features using this particular approach, and we can use the carboxylic acid to immobilize then proteins, in this case fibronectin. And so the idea is we're going to take these stem cells and let them be exposed to these types of libraries and ask, do certain parts of the library affect different types of processes? So again, you have a challenge when you make libraries with nanoscale features, when that becomes one of your variables, because you have to have a readout, right, that's macroscopic. Well, the cell in this case becomes the readout. And when we find an interesting area, in principle, we can level the array and duplicate that so that we get statistically significant data. So we can use this as a rapid search type of protocol and then go through and refine and ask, was that really important or not? And so just to make a long story short, we look at this across a range of feature sizes. We went, I think, from about 100 to a few microns. I'm just showing you a little glimpse here. And then the person doing this work, Louise Guillaume, inspects these, and she notices that in certain parts of the array, it looks like we're getting a large amount of differentiation towards osteocytes. And so she then goes through and does the leveling experiment, and she begins to then build duplicates of those size features. And what she noticed was that small features posed more stress, it seemed, on the cells than larger features, and caused them to go down this osteocyte differentiation path preferentially. And so we wanted to not just do that by eyeballing, but to actually have real chemical markers that either proved or disproved that particular observation and conclusion. And so here you can see we're looking at cells where we've selectively taken them down the osteocyte path. And there are a couple of controls here. One where we have a negative control, right? No osteogenic media, that's OM is osteogenic media, and no nanopattern. One where we have nanopatterns where we have micron scale features or 300 nanometer features, and one where we have osteogenic media but no nanopattern. Okay? So this is the best that the biologists can do, and this is what we're effectively doing here. What we find is that the micron scale features do not give you selective differentiation, but the 300 nanometer features do, something that would be completely lost without doing this type of experiment. It would take you forever to go through and analyze all of the different types of things that she analyzed in this one very simple experiment using this tilted array approach. Here she's using a marker, real-time PCR measurements of osteocalcin to show that this is not, again, just her observation in terms of morphology, but that there is, in fact, raised levels of osteocalcin. It's actually raised even higher than the positive control. So that's kind of interesting. And then to be absolutely sure, we looked at a second marker, alkaline phosphatase, also an indicator of osteocyte formation. And again, you see very similar results. Elevated levels with the 300 nanometer features, but not with the micron scale features. And again, higher than what we see even with the known osteogenic media that causes this type of differentiation. So that's kind of an interesting capability. And I think what we're now posing to the biologists, we're asking people to take this type of tool and use this, and use a nano or size, in this case, is another variable that can be used and implemented in your types of combinatorial libraries and analyses, because I think it's going to become very important in lots of different types of processes as we go forward. It's just not something you even consider because you don't have access to it. Now, one of the things that you lose in terms of capability when you go to polymer pen from dip pen is resolution, because these tips are not as sharp as the tips made with silicon features. But again, this idea of moving the tip to the spring is quite powerful. And we thought about that, and we said, hey, if that's good, maybe what we could do is move the tip, or move the spring. I said move the spring to the tip. If we move the spring to the backing layer, we could put hard pyramids on here, and you kind of think of this as hard pyramids floating on soft springs. And you can do that. And so, again, all the microfab that we learned at MIT and have continued, I'm not going to go through this process, but you can very quickly fabricate silicon tips on the soft PDMS backing layer. And so this is going to be a little bit different from the polymer pen. Now we have the springy backing layer, but not a springy tip, but we can also make these much sharper. We can take these down to about 22 nanometers in terms of radius of curvature. If you look at the literature, I think you can convince yourself that these will be able to get down to about 10, but that's the best that we can do right now. So fundamentally, though, you have a different phenomenon, right? Because now you are printing via diffusion. You're getting them all level because of the soft backing. But this is more like a dip pen type of experiment. Feature size is going to increase with contact time, but it's not going to matter how hard you push, at least until you break the tips, because you're not compressing the tips, you're compressing the backing layer. And so what that gets you then is much higher resolution. So this is the pyramid off a US $1 bill. You can see done 55,000 times, sub 50 nanometer in terms of resolution. And again, the duplicates, remarkable, all the tips effectively working. I have people that come through the lab. We can look at some of these with a high-powered microscope, and you can pan through the whole area. You find very few defect sites because of this alignment procedure that I introduced. Okay, so one of the things that really bothered us, though, was how do you get to smaller features, right? As a chemist, I really wanted to see, push this towards the molecular length scale. How could you go to the sub-10 nanometer limit? We could never do that. We tried everything. We tried using carbon nanotube tips. The meniscus limits you. The flattening of the tip limits you. There are all sorts of things that dictate or that cause the structures you intend to generate to be larger typically than 10 nanometers in size. And so we began to think about this and said maybe what we have to do is combine chemistry with these types of approaches. And we came up with a technique we call scanning probe block-copolymer lithography, which I think is going to be very powerful both from a nanofabrication standpoint but also from a fundamental science standpoint. So here's the idea. You can take a page out of the block-copolymer literature. You can synthesize block-copolymers that have these polyvinyl pyridine groups that can sequester metal ions, for example. You can disperse these in solvents, form micelles. You can load them up with metal ions, in this case gold. You then can coat tips, cantilevers, or any of the types of tips that I showed you, and you can then transfer a feature to an underlying substrate. Now, what's that going to do for you? Well, that's kind of interesting because what it does is it creates a reactor, a little nanoreactor, where you can precisely control the number of metal ions that can be involved in a given synthetic step. Because it turns out under a certain size, every metal ion in that feature will coalesce and form a single crystal nanoparticle, which is shown here. So if we take then and treat this with a plasma or heat it, what you end up getting are these single crystal nanoparticles. And if you vary the polymer volume, the feature volume, you vary the nanoparticle size. And roughly under these conditions, it's about 1/10. We can also control the loading to some extent. There's going to be a situation where I think we're going to be able to get down to a single atom per feature. It'll open up a whole new area in terms of controlling how chemical reactions occur from the bottom up in this case and how you site isolate where different types of structures are. So here, if you look at this, this is, again, very scalable. I don't think we could, and we do a lot of synthesis, I don't think we could synthesize nanoparticles this regular. So these are 4.8 nanometer plus or minus 1/10 of a nanometer gold particles. Every one is a single crystal, okay? And you can do it over large areas using the polymer pen type of approach that I showed you. The other thing you can do is you can cool this process down. And in the electron microscope, you can follow the ripening process. And so I'll just show you real quickly here. And you can see this is a movie where this central particle, as we raise the temperature, is eating all of the atoms and particles around it. It's going to consume that pretty soon as the single crystal particle is ultimately formed. Okay? So it's just about to go. There it goes. Okay? So now you can freeze this out, and this is actually more informative. You say, well, big deal, what do you do with this? This, I think, is going to be a fantastic surface science tool because now we can get snapshots of, I always feel a little bit, I'm teaching general chemistry now, a little bit illegitimate when I'm teaching because I talk about things like Ostwald ripening. I've never seen Ostwald ripening. Well, now you can watch it, okay? And you can also differentiate it from coalescence. So there are two types of processes that we have to be concerned about. One is the fusing of particles, and the other is a particle that's coalescence, and the other is a particle that undergoes true Ostwald ripening, where you've got two particles, and one shrinks, and the atoms from it go to the other, and it grows at the expense of the other particle. Well, it turns out you can look through these maps, these trajectories, and in this particular experiment, you can actually figure out when coalescence dominates and when ripening dominates. And it's all distance dictated, and that kind of makes sense. Greater than 5 nanometers, you have much greater ripening than coalescence. Less than 5 nanometers, the particles tend to fuse like I showed you in the movie. And so I think this is going to be powerful in terms of understanding a lot about nanocluster synthesis and growth kinetics and mechanisms. And I'll show you one other one that's kind of interesting here too. So that's the good news, that you get this fantastic reproducibility with gold, and you have all these abilities to map trajectories and things like that. But it turns out when we started looking at other materials, we thought we were going to go across the periodic table. Nothing else worked. Okay, so you put platinum, it doesn't work. You try silver, it doesn't work. Why don't these work? Well, I asked a postdoc to figure that out. I had a guy who came from Wisconsin, who came from the block copolymer area, and he's an engineer, and he thought about this in both a science and an engineering way. And he said, maybe this is a mobility problem, right? Because other types of metals have higher melting points. And so maybe what happens is when you reduce, you form a lot of nucleation sites, but you don't get that ripening effect that I showed you, and you can't get to the single crystal nanoparticle that we're ultimately after. And so what he found was that that is in fact the case. There are two key steps in this process. When you heat the polymer to affect the reduction, the salt will aggregate and phase separate. That's critical because if that can happen, you can then get the salt, the atom precursors, close enough so that the ripening event can take place. If you ramp up rapidly, like we did in the gold case, with other types of metals that have lower mobilities, you just form a lot of nucleation sites that are locked out. Okay, and I'll just show you that over here. You can see here, this is the type of thing that you see, for example, with something like platinum, or even if we do it really rapidly with gold, a lot of nucleation sites, but we don't get the nice single crystal nanoparticle, where if we go slowly, we can get pre-aggregation through a low temperature regime and then ramp to a higher temperature regime and then get reduction and get the nice single crystal particles that I showed you. And so we've now used this, and we can go now across the periodic table. We can use this mechanistic insight, and by using the right types of protocols to, again, separate the aggregation event, the phase separation event, from the reduction event, we can make gold, silver, platinum, palladium, iron oxide, cobalt oxide, nickel oxide, copper oxide. You can even do alloys. And so this, again, idea of controlled synthesis, I think you're going to be able to put with tri-block copolymers, for example, different types of materials that can be, have controlled stoichiometry and be synthesized from the bottom up. Okay. The last thing I'm going to show you and share with you is a really neat recent development. This is the one I think that really will open up that idea of a desktop fab. So the other thing you can do with these pyramid arrays is you can coat them with a polymeric material. I'm sorry, an opaque material like gold. So we have a polymeric array, a PDMS type of array, coated with a thin layer of gold. And if you etch the tips, you can transform this now into a system that acts like a massively parallel NSOM. Okay? So here's an example. We did this initially where we could then bring light through the back of these pyramids, just an LED, and we could expose a photoresist underneath, and by moving the array over the PDMS or the resist-coated substrate, we could effectively do photolithography both in the near and the far field. And so this is a Chicago skyline done 15,000 times. Okay, duplication tool, wonderful. But not really what you want for a desktop fab, because you'd like to be able to make not just duplicates, you'd like to be able to make anything, right? Well, to do this and do this well, we have to come up with a way of making these tiny little apertures uniformly. We can do that by taking and spin coating a polymer on a gold-coated PDMS a tip array. We can ion etch and expose the tips. We can then wet etch the gold, lift off the polymer, and now we can get very uniform tips or apertures across the entire array. So now you can begin to put this into the instrument, bring light through the backside, squeeze it through those apertures, and this is developing then photoresist. As we move across here, you can see we can control and make any sort of structure we'd like. Lines, dots, by controlling exposure time, we can control the size of the features as well. And again, very, very uniform from tip to tip to tip, and that's absolutely critical if we're going to think about this desktop fab capability. So here's kind of the neat idea. I have a projection theater in my house. And one of the postdocs was over. We were watching a movie, and he said, you know, those projection systems, as you know, have this digital micromirror device as the backbone behind it. And you can effectively take a beam of light and split it up into hundreds and even thousands of different beams of light. And so what we thought about was we said, hey, we could take that device, which is dirt cheap. It turns out you can get it for less than $100. And you can take an ordinary LED, split it up into many beams of light. And as I said, although these are typically nanoscopic, 100 nanometers, for example, in size, or smaller, we can go down to 2 nanometers in certain cases, the backs of the pyramids are microscopic. And so the idea is we can begin to take that device, split a beam up, and then channel selectively through the different types of tips. And that then might be able to give you the ability to stitch together fields and build structures rapidly over large areas, but still maintain very, very high resolution. And so we built this system. We have it now at Northwestern, and I'm not going to go through all of the alignment procedure, but it's a kludged together system from a scanning probe instrument, a projector, a digital micromirror device, and a bunch of software that we wrote for alignment. Alignment's absolutely critical. You have to again, have the array perfectly parallel. But once you get the system fully aligned, you now can begin to do some interesting things. So this was the first interesting thing. They wrote Hello World in 64 different languages simultaneously. So this is developing a photoresist where different pens are making the different words simultaneously. And if you don't work, this is a kind of a tour de force type of example of scanning probe. There are, put it this way, prior to what I'm going to show you, there have never been things that are macroscopically viewable produced by any scanning probe technique. It's my postdoc, right, when he was taking a picture of some of the structures I'm going to show you with his cell phone, he said, I think these are the first macroscopically viewable structures ever made by any sort of scanning probe technique. And so actually, here's the first one. This is the London Olympic logo. Not so impressive. You can barely see it here until we look at it under higher magnification. And here you can see the rings. We look a little bit closer and superimpose. This is millimeter in terms of length scale. He now has all the sports icons that make up the rings in nanoscopic features embedded within it. And again, the point of that is to show that you can go across multiple length scales. And again, think of that capability and where it exists elsewhere. But what about more functional things? So here he made, these are planar inductors made up with 63 different pens. You can see here, these are the 63 fields written by these, stitched together. Again, the alignment's critical. These are all working devices, serpentine resistors, even a Northwestern resistor. And so simple electronic devices now being made. The other thing you can do with this is kind of interesting is this is a Charlie Lieber type of experiment. The guys in the silicon nanowire area, they'll make these very sophisticated architectures where they'll take a few nanowires and they'll hardwire them using e-beam lithography so that they can make measurements on those structures. What they don't tell you is they spend a ton of time going to an e-beam to actually find these types of structures and wire them up one at a time. Here, what Keith Brown did was absolutely spectacular. The wires, although, again, they're nanoscopic in terms of diameter, they're microscopic in terms of length, and you can see them, at least the fringes of them, with a high-powered optical microscope. So he scattered wires over this substrate, which had a lot of contact pads, which we then can wire up to make electrical measurements. He scattered the wires, which you can barely see, you're going to see in a second. He then imaged them, right, and created a pattern, so he knew where they were, coated them with a resist, and then wired them up using this beam pen lithography type of technique. And so here you can see those structures. 59 out of 60 patterns successfully transferred, 40 out of 60 of the devices are functioning. Again, for a first type of experiment, I think fairly impressive, and beginning to make me a believer that this type of technique, if we're going to see any sort of scanning probe tool really move towards a desktop fab capability, this one is a pretty good candidate. And so this is kind of now the timeline as we go. And as I said, I think if we went back here and both looked at this, we'd say that this type of array architecture is really a good way to go. But sometimes it takes a lot of trial and error to find an architecture that ultimately works. I think that when we look back at this is going to be very important in terms of moving scanning probe lithography, at least, from just an academic curiosity among a few people to lots of different folks. Some of this stuff's been commercialized now, and because of that, and also some of the capabilities that we've developed, it's now in literally hundreds of laboratories around the world, and you'll just see mostly in terms of research use. But I'm hopeful that with these new types of discoveries, we're going to see production capabilities as well. I'm going to just conclude by acknowledging the folks that have done the work. This is my group back at Northwestern. This is actually the DPN subgroup. A lot of really fantastic and talented people. Keith Brown, I think he's in the back here. He's actually in the job market right now. Just absolutely spectacular postdoc. Came out of Westervelt's group at Harvard. He's actually a physicist that works in a chemistry group, but he's done beautiful work in terms of interfacing his skills with many of ours to move this forward very rapidly. Funding was provided by lots of different agencies, but primarily the Air Force and DARPA through their tip-based nanofabrication program. And I'll finish just by saying congratulations one more time. Well-deserved honor.
Questions?
So, one thing you can do with inkjet printing is print different grayscales. And here with the polymers, for example, depending on the molecule that you ink with, presumably you get different amounts absorbed into the polymer. So is it difficult to control grayscale?
With polymer pen, yes.
Okay.
With beam pen, maybe not, because exposure time can be a tool that allows you to build. We haven't tried a lot in that area, but polymer pen, absolutely. We try to go to saturation with polymer pen, right? Because that's everything can be taken to, the same endpoint in terms of molecules per unit area. And in fact, you find in terms of monolayers, you tend to get much more well-formed structures than even conventional monolayer formers because you have a huge concentration gradient. You're basically hovering the adsorbate and a large concentration of it right over the substrate. And so a lot of defect architecture gets corrected and everything gets filled in very rapidly. Hey, George.
You've used over this course of, whatever it is, a decade or 15 years of development, a whole host of really interesting techniques for doing things. The question is, how at this stage does one decide which one to push forward and spend the extra $50 million to get really, reality in whatever form?
Well, it's actually, that's a great question. I mean, unfortunately, that happens with sometimes multiple generations. So Nano Ink bet heavily on the traditional dip pen with cantilevers. What they developed in the process was a great research tool. It had about a $10 million annual revenue. Nothing, spectacular, but substantive in terms of research tool capability. And they were getting a lot of pickup. That's one of the reasons there are so many groups on the map. It was through their efforts. The problem with conventional dip pen is what I said. I think the speed, it's too slow. When you go to the parallel arrays, it becomes too fragile and too expensive. So they were building 55,000 pen cantilever arrays and selling them at $10,000 a pop. I mean, imagine being an advisor, even for research purposes, and having your students saying, ooh, I just dropped the array and we're out 10 grand. It's not a good thing. Here, and that's why I think this is, both from a research standpoint and from a production standpoint, is really going to accelerate things, because now this is turned the accessories, the razor blades in this case, into a very affordable type of structure, and one that has a tremendous flexibility. So it's almost a disposable system. You just throw it away after you're done with it one time. You wouldn't do that with a 10,000 pen cantilever array. Nano Ink burned through about $150 million, right? And so they got a great research tool out of it, but not a production capability out of it. I think it's going to take another $50 or so million. The good news is probably not another $150 million, but you have the hindsight and the good fortune of being able to look back and say, oh, I see, I probably don't want to go the cantilever route. This wasn't available to them at the time. I think had they bet on the cantilever-free approach, they would have ended up at a very different point. I mean, it really does merge the strengths of what you've done and some of the things that we've done to create I think, a pretty powerful capability that spans multiple length scales. Yeah, so you're talking about with the scanning probe block of polymer lithography. So one of the things that's interesting about that is we can't control where the particle ends up, right? So you make a big feature, but the particle is much smaller than the big feature. It could end up on the edge, it can end up in the middle. So in terms of, we lose a lot of registry in that. So that's one problem. So I don't think we're going to be able to come back with tips, at least with the current system, and modify those. What we're using them for, though, which you might find interesting, if you do the tilted array experiment, you now can build a gradient of polymeric features and therefore a gradient of nanoparticle sizes. And you can build libraries of nanostructures where everything is positionally encoded and where you have systematically dialed in what you want in terms of composition. And so we're using that to begin to explore whether or not we can discover interesting catalytic reactions that depend upon particle size, shape, and composition. Hard to do right now. Very, very hard to do. I would say that we can't do that yet, but a good challenge. I mean, a lot of this is you get push things forward by thinking about, not what you can do, but what you can't do.